Hi, in this video, we want to talk about logistic regression residuals, leverage, and influence analysis. All right, so the goal of this video is to go over ways that we're going to check about individual data points that have more of an impact on our model than others. And basically, this is going to be talking about like, hey, we're going to flag data points to double check to make sure that everything is on the up and up. If everything's looking good, don't worry about it, move on, keep rocking it. But this is a technique to detect problems that maybe the data is wrong. Maybe there's an error in the recording. Maybe there's an outlier. Maybe somebody cheated on the data. We don't know. But I'm going to go through this process. I'm going to try and find potentially problematic data points, then do something about it. What can I do? I can omit the data point completely, or maybe I'll change its value to something that's a little bit more reasonable. So if I was expecting numbers between 1 to 100, I see 1,000, I could drop that down to 1,000 instead of removing the entire data point, muting it down, or I could treat it as a missing value and replace it altogether. What we do depends on our situation, what we feel is best judgment. All right, so major aspect about this is a big point. I'm going to repeat this over and over and over, is that we do not have the distribution assumption for linear regression. So we have no assumption about that normally distributed residuals. Remember, in logistic regression, we are not modeling the individual observation, we're modeling the expected value. In linear regression, we're doing both. And so because of that, we don't actually have a distribution to work with for the analysis. So as I work through this, what's going to end up happening is I'm not going to actually have the same oomph that I would have if I was doing linear regression. What we're going to do, we're going to flag the extremes. And when I flag an extreme, I'm going to go, hey, I want to double check these data points here, make sure that everything is on the up and up. All right, so we cannot use the same techniques that we use in linear regression because I don't have that distribution aspect, that assumption. So I don't have a probability distribution around my residuals, but there are techniques I can still use. So what we're going to do, I want to identify the extreme values, which points that correspond to an extreme residual, extreme Cook distance, or extreme leverage, and then just double check those points. All right, so the residuals, I don't have the assumptions of their distribution like I do with linear regression, the normally distributed mean zero constant variance with respect to predictors. Most of the linear regression residuals do not provide, or sorry, never mind about that. So there will be Cook's distance. Cook's distance evaluates the difference if an observation is omitted from the data. So here, what I'm going to do, I'm going to fit my model with all my data, and then I'm going to look at the coefficients. Then I'm going to refit the model, but remove that one observation. Look at the coefficients. If I see a big change in the coefficients, then I know that there is something going on with this that is having more influence on what's going on than other observations. It might be that this might be like a rare occurrence, very normal, very natural, or there might be a mistake, there might be an error, there might be cheating. We don't know. We have to double check it. So we don't have the theoretical aspect that we have in linear regression, but we can still use Cook's distance because we know extreme results are ones that we want to double check. Now, leverage, something about leverage is that the hat matrix doesn't consider the target variable at all, in no way, shape, or form, regardless of me using linear regression or logistic regression or whatever. And so leverage can be used similar to logistic regression for the purpose of identifying extreme observations. So leverage, that it's going to show observations that have more influence and more pull than others. Now, I lose the theoretical aspects with that, but I have a method of flagging extreme values, and that's usually enough operationally. All right, so let's go ahead and set up our workspace. I always like to do piping for the tidyverse, reducing the number of digits, avoiding scientific notation, and make sure my workspace is clear. And I'm going to use the chronic heart disease data set. from the SA Hart or the SA Hart data set from the elementary statistical learning package. And I'm going to convert the family history to its dummy variable presentation. It's got 2 levels, and I'm just going to say, hey, let's just put it as 0, 1 to make it a little bit cleaner for fitting the model. And let's go ahead and fit this model. I've fit this model a bunch of other times in these videos. We should be familiar with this. And you can see we have almost everything is statistically significant. Obesity is not. And it's going to be, this is going to be correlated with the cholesterol and with age on this one. And so, you can see what we got for our model. So now let's go ahead and check out our likelihood ratio stats. So here I've got my AIC, my BIC, my likelihood ratio chi-squared, our degrees of freedom, and the probability of getting that chi-squared or greater. All right, so here, if I see a large, so if I see a large p-value, that indicates that there's not a lack of fit. If there is a small p-value, that indicates that there is a lack of fit on this particular test. So here we're good. We're good. All right, so the first one I'm going to show you is what I consider the most important plot of residuals for logistic regression, Cook's distance. All right, so you'll notice that when I plot a linear model or a generalized linear model in the x position, by default, I'm going to get 4 plots. If I don't specify which ones I want, I use the which keyword to specify which one we want. Now, there are 6 possible plots, 1 through 6. There are 4 of them are by default. And here, something I always do is you'll notice that I change the color by my target variable. I always change the color by an important variable to help spot things potentially. And so here, the red is where in the data set they have chronic heart disease, and the black is where they don't. And so we can just see Cook's distance. And so the independent variable for this one is which row number are they on there. And so this gives us a way of like just trying to spot where in our data do we have extreme ones. R always flags the 3 most extreme every single time. Okay, so if I have a small data set, let's say I have only 5 data points and I'm fitting a model, it's going to flag 3. If I have 1,000,000 data points, it's going to flag 3 every single time. So when I see 3, I don't immediately say, oh, all of these are a problem. I know this is flagging the most extreme ones. If I have a large data set, it's probably missed some. If I have a big data, if I have a very, very small data set, then some of them, maybe all of them, aren't problems at all or not extreme. It's just that R always flags the 3 most extreme. So just keep that in your mind as you look through here. But this is saying observation 1782 and 261. One thing I could do if I had like an ID number, if I had an identifying value, or maybe the name of the location, name of the state, the person's name, something like that. If I put in the row names to be that identifying column, then boom, I would get exactly those here. And that's true for all of the plots in base R. All right, now the next one is that we're going to look at leverage on the x-axis, Cook's distance on the vertical axis. Remember that leverage doesn't take into consideration the target variable. It only considers the predictor variables. And so here, I have no distribution assumptions about these. And I feel like these two are the most important ones to look at for this purpose. And you know what? You'll notice I've got 1782 and 261, 1782, 261 once again. All right, so this is an indication that maybe I want to consider those. Those have large Cook's distance, and this plot involves Cook's distance. So it's not really surprising that they're coming up again. All right, so residual visualizations. This is an important aspect of like really digging into the model. And so there's various types of residual plots that help us identify issues. So something that we're going to be looking for is that nonlinearity. So if I can visually see a pattern, I will consider doing something about that. Maybe incorporating like a quadratic term or maybe an interaction, a square root term, maybe transformation, just something like that. There are also heteroscedasticity, something I'm looking for, non-constant variance with respect to the predictor variable. And here also outliers and the need for a transformation, like that, maybe a log transform or square root transform, something like that. All right, so now let's go ahead and look at residuals versus fitted values. And so here, and so this is a plot 1. Here is the predicted value, and this is before we convert to probabilities. This is using the logit, and then here is the residual. Now it's always going to work out that we're going to have 0 on one side, 1 on the other. So all of these are 1, all of these are 0 on here. And so we see this. So we can see that we've got the 3 most extremes sticking out are over here. And so, that's just something to consider on this. And we see 261 once again. Right? We're probably going to see these numbers again in future plots. And so this curve here, if I was doing linear regression, this would be a big deal. This would be a problem. We would slam on the brakes. Logistic regression, it's okay. This is fine. We have no distribution assumptions about the residuals. If in linear regression, if I can see a pattern, there's a problem. Now, normal QQ plot, this really is not nearly as useful as it would be in linear regression. We don't have the assumptions that we have in linear regression. And so this plot doesn't have really much meaning to it. The thing that is most important to us is, what are the 3 most extreme? Basically, if they're extreme, then even under like a different distribution, they're going to probably be extreme under that distribution also. And so if it's sticking out really far, then I want to consider like looking into it, digging into it, seeing what's going on with that particular value. All right, so now the curves are to be expected, and a perfect model would have residuals close to 0. And so for us, we're just trying to find extremes where either I'm going to modify the value or omit it. So I can either impute it for modification or mute it down, reduce it to be less extreme. And so we see the same values we saw a moment ago once again. And we can see that the ones with chronic heart disease and not heart disease over here. And we have no assumption about the distribution. This is clearly not normally distributed, but that's fine. That's not an issue because we don't have the assumption of normality. So really that plot just says, hey, your residuals are not normally distributed, but we didn't assume that anyway. That's really not an issue. All right, next one is the scale location plot. And so we're going to, once again, for us, we're looking for extreme residuals. And so we see 261, 113, 475, and this is the square root of the absolute value of Pearson's residual. So Pearson's residual, take the observed value minus the expected value or the modeled expected value, and then divide by the standard error. Okay, and so then we're taking the absolute value here, and so the standardized Pearson residual, it would be like between -3 and 3, but then we hit it with a square root to make things a little bit easier to interpret. And with the absolute value, forces them onto like the same region. They wouldn't be crossing if we did not take the absolute value here. And basically, once again, we want to look for the extreme values. Like this 261 is, I'm getting really, really interested in this point right now because I think it's been on every plot so far. Now, Cook's distance, here we're trying to find the influential observations. And so this is what we're doing. We're computing a distance based off of how much do the coefficients change when I remove that one data point. If it changes a lot, that data point has a lot of influence. So points with high Cook's distance are influential to the coefficients of the model. And so we've already seen this plot. But to me, it's the most important one for logistic regression. Now, we can also look at the residuals versus leverage. All right, so leverage is, a measurement, we're using the hat matrix to measure how much influence does an observation have on my model? Is it pulling the model towards itself and away from other observations? That's a high leverage data point. And so when we see that, that doesn't mean it's wrong, but we want to double check, our data, make sure that it's correct. And so here we can see vertical axis is the standardized Pearson residual, and then the horizontal axis is the leverage. And so we see asymmetry in here. So like this, maybe there's some curvature here. There might be something going on. Maybe I want to add like a higher degree term or a transformation to improve this. Now we can also look at Cook's distance versus the leverage. And this is plot 6 on this one. And this one shows the contours of the standardized residuals that are equal to, in magnitude, to the leverage or the proportional aspect. And so here's the contour. And so, this is indicating that 261, once again, is more extreme than the rest in terms of that contour because it's got a larger contour value. All right, so now partial residuals by the components. What we're going to do is that we're going to take our partial residuals and we're only going to look at the partial residual for that particular predictor variable. And then I'm going to plot the predictor variable along the horizontal axis. Now here, this is not the best way to plot this. I really should have done a box plot, but I'm trying to be consistent, so I didn't bother with that. If I saw a big difference in those box plots, that would be an indication of a problem. Now here, there's a little bit of a curvature up going on. And here we can see that there's definitely more of a variance on the positive cases in this region here. So that's for that type A aspect. But I don't see like a transform that would correct this. Probably if we had like there might be another predictor variable or maybe another transformation, something I could do to get rid of the slope that I'm seeing here. But it's not that severe. All right, so here I see a curvature here. So maybe I would want to consider like a quadratic possibly off of this. I see, once again, maybe there's a curvature here. Maybe I would want to consider a transform on cholesterol. Obesity, I'm not seeing anything that strong. All right, now here, possibly something going on. All right, so by looking at this, for obesity, I chose to go ahead and just see, hey, let's go ahead with this curvature here. Let's go ahead and add a quadratic term. And by doing that, put in a degree 2 polynomial on obesity, my AIC decreased slightly. I mean, it was an improvement. It wasn't much of an improvement. So, keep it, lose it, whatever. All right, so now the bend residual plots, what this is going to do is that this is going to take averages and then after bending the FID values, and then there's going to be a 95% interval putting around the plots. And so if we're outside of the bounds, then that's an indication that I want to investigate further into that bend. And so here, 1 point is sticking out of the region, 95% intervals means that some will 5% be sticking out. I consider this okay. I wouldn't do anything about this. Now cumulative residual plots. So here we're going to try and look at the goodness of fit using the cumulative residual plots. And so we're going to look at one of the predictor variables or the fit values on the horizontal axis. And so deviation from a horizontal straight line indicates a poor fit. And this is, now, when do you actually say that this isn't, this isn't good enough? I don't know. The ideal plot would be, the black would be perfectly horizontal. We've got a decent p-value on this one. All right, so here, perfect would be horizontal. All right, not statistically significant p-value. And so here, not statistically significant p-value. So it's, we're still rolling with it. Oh, this is huge p-value. Look at that. And, we just can keep on scrolling through, looking at all of these. All right, so now for your homework, I want you to go through. I want you to do a logistic regression model, and I want you to visualize plots 4 and 6 from base R's plot function when applying a generalized linear model, and interpret the plots. So, not too heavy of homework. Just go build your model, build the plots, reach a conclusion. That's all I've got for you. Life is short. Do math.